Before I start this video, let me take 30 seconds to tell you something about Exergic. Exergic is India's most trusted and most experienced institute for online GATE preparation. I am Chandresh Mahajan, founder and chief educator at Exergic. I am an All India rank 37 in GATE Mechanical Engineering, an ex-Indian Oil officer having 7+ years of teaching experience as of now. These are the GATE 2021 Mechanical Engineering toppers from Exergic. You can find their preparation strategy on Exergic's website. To know more about our GATE courses, you can visit our website or contact us on these details. Also, you can download Exergic GATE preparation app from Google Play Store. The link is available in the description of video. Now let's start the unit of rolling, or you can say rolling motion. This is a very important and very crucial unit of engineering mechanics. And trust me, it is such a unit which is not clearly understood by a lot of students who are appearing for GATE or who have cracked GATE even with a good rank. Because this is such a topic from which a variety of questions can be made, both simple as well as very conceptual and good difficult questions. And generally GATE has been asking very simple, very direct questions from rolling, as a result of which students were not preparing completely, fully for rolling the way they should. But in recent years of GATE, some very good questions have started coming from rolling, which requires a very good grip, very good command over this unit, okay, and very good in-depth conceptual clarity. So this unit has become even more important, and you can say trending in terms of its relevance in GATE examination. And again, it is such a unit where it's very simple, but there are many small concepts involved to get a full clarity, full understanding of this unit. Okay, it is not like some other units of mechanics where there are generally handful of concepts to remember. It is such a unit where you need to have a good conceptual grip over a variety of concepts in order to totally understand this unit. Okay, but let me tell you very clearly that although this unit confuses a lot of aspirants, but this is a very easy and again very interesting unit, just like many other units of mechanics or other subjects of mechanical engineering that we have been studying. And if you complete this unit, by the end of this unit, I guarantee you that you will not only start liking rolling a lot, you will not only develop a good confidence in rolling, but also you will be able to score complete marks in this unit, from this unit. Whatever question has been asked or can be asked in GATE from this unit, every question, theoretical, conceptual or numerical, you will be able to solve with full confidence if you complete this unit with me. Okay, so without talking much, let's start this unit. Okay, look, one of the most important inventions of humankind, what do you think what these were? If I were to list top 2 inventions or top 2-3 inventions, then obviously fire will be one of those. Invention of fire, invention of different tools, right, would be another, and invention of wheel would be definitely in top 3 inventions of mankind, of humankind, right? And why the invention of wheel was so much important, what exact feature of wheel is useful for us, became useful for us then and still useful? Its ability to roll, right? We have wheels that can roll very smoothly, very easily, and we can carry things over them when we make them an integral part of different vehicles. This is just one example that I am giving you of wheel. There are many examples present, right? I am not restricting this application of wheel just to vehicles. We know there are multiple examples and applications of wheel, but it is one of the most common and one of the most widely seen application, right? And as I told you, why wheels are so much important? Because they can roll, right? and the motion that those wheels do, roughly we can call that motion to be rolling. Okay, although they can perform some complex motions as well other than rolling, that we will be covering in this unit. But to generalize this, to just give you a simple idea of what motion they perform, we can clearly say that the wheels perform rolling motion, right? They roll ahead or maybe backwards also. Now, in this case, before we begin this unit and before we understand the detailed concepts of rolling or rolling motion, there are two concepts that you should note down, or I won't say them as a concept, but two special note that you should write down in your notes right now, that will be valid throughout the discussion of this unit. First note is that whatever discussion we are going to do, whether I am talking about wheel here or whether I have made a disc here, whatever discussion I am going to do will be applicable not only for that particular shape but for any other shape as well which can roll. For example, if I just talked about wheel, that wheel can roll, it doesn't mean that only wheels can roll. Disc can also roll, cylinder can also roll, sphere can also roll, right? Every such element which has the capability to roll, that discussion, the discussion that we are doing here, will be applicable for each of those as well. Okay, in general we will be taking the example of disc to explain you different concept, but it can be equally applied to sphere, to disc, to some ring, to some cylinder, to a hollow cylinder. Whatever shape can roll, just like the disc or the wheel. Alright, this was first point in your note. The second point in your note is, and this is the second point, is such a point that I have already told you in the beginning of mechanics, but let me repeat it here, that we consider these rolling elements to be rigid, right? We have already discussed in detail what is meant by rigid, why we consider rigid bodies in mechanics, and why we consider deformable bodies in mechanics and strength of materials. So that discussion I am not going into right now. We have already done that. But it is important for you to know that whatever bodies we are considering that are rolling are going to be taken ideally as a rigid body. What does it tell us? It tells us that at the point of contact, means the point where they are touching the surface on which they are rolling, at that point there will be just a point contact or a line contact. If it's a sphere, so it will be touching it at a certain point, or if it is a cylinder, it will be touching it along a line, which is nothing but a combination of points only, right? Or in 2D, if you look at cylinder and you just define the cylinder in 2 dimension only, then you will simply say it as a point contact. All right. So they will be, these bodies will be touching the surface at a single point in this study, 2-dimensional study that we are doing, right? Now, do they touch the surface at a single point in reality as well? No, because in reality, every body, we have considered that, we have discussed that already, that every body deforms. Even if there is no external force, external load, it will deform under its own weight, under its own load, right? So there will be certain deformation in reality at this point of contact. So this exact point will not be a point, it will be an area in reality, right? But for the study, ideal study, theoretical study that we have to do, we will consider this particular area, this particular point to be only a point and not the area. Now, what happens when it is an area and how the theoretical, the ideal study that we are doing differs from the actual one, that I will definitely tell you. That what happens if it is actually an area, which it is. In real cases, you see, if you look at any tire of a car, it is not touching the road at a point. You will see a proper area on which it is touching, right? The bottom part will be somewhat flat where it is contacting the road. So we know that in reality, it is not a point contact. So things can change, things will change. Then what we are going to discuss, but how they will change, that I will definitely cover in this unit. But from the point of view of whatever examination you are writing, the discussion of rolling or rolling motion In that discussion, we consider the body to be a rigid body such that it touches the surface only at a single point and not on a complete area. These are the two notes that I want you to know even before we start discussing it. We have not yet started the discussion of rolling, right? So these are the two special notes that you can write in the beginning of it. Now, if I ask you that there is a wheel like this which is rolling forward, okay, and if I ask this to a group of students, to a group of some young students, so what they will respond? Some of them will tell that this motion is a straight line motion. It's a translation motion, right? This wheel is moving forward, and they are correct. It is moving forward. You cannot deny it. It is at this point at a certain time, and as it keeps on rolling, it reaches some other point. So it is definitely translating, correct? But some of them will say that, sir, it is not only translating, but we can clearly see that it is doing circular motion as well. Because whatever point is at the top right now, as it will keep on rolling forward, the topmost point will come at the bottom at some point, at some time, and then it will again move back to the top, right? It will keep on performing circular motion about its center. They are also correct. They are also not wrong. But what exactly and what type of motion exactly is this rolling body performing? Is it a translation motion or is it a rotation motion? It is a combination of both of them. Rolling motion is a composite motion. It is neither pure translation nor pure circular motion or rotation. It is a combination of both of them, right? And this is such a concept which is very basic, and I think some of you or maybe most of you will be knowing about this concept already. It is such a basic concept, right? But trust me, even if you know about this concept, you don't know it good enough in right depth, because whatever discussion we are going to do further in this unit, we will be talking about slipping, skidding, sliding, accelerated rolling, uniform rolling, what is the effect of forces applied at different points, torques applied at different points. Every study we are going to do such that whatever question is going to be asked in GATE and can be asked in GATE or has been asked in GATE, you can easily solve that without any trouble. And trust me, in all of these discussions, this basic concept that rolling is a combination of translation and pure rotation is going to be there. But how it is going to be there, in what form we are going to use it, that is going to be very interesting to see. Okay, but this is a very basic concept known to many of us, but we don't know how to actually apply it. Okay, so you can write it down again in your notes that this rolling motion, the pure rolling motion, is a composite motion. It is a combination of pure translation and pure rolling motion. How you can see it? If I just want to see the pure translation motion, what can I do? I can stand on this surface, right? If I look at this motion from the frame of reference of this surface, if I am standing here, and if I consider this whole body to be just a single particle, a simple point mass, then I can clearly see that it is moving forward. So that is a translation motion from the point of view of someone who is standing on the surface or who is at rest, you can say, okay, from his frame of reference. But suppose you are sitting on the center of this rolling wheel. This is rolling forward and you are sitting on the center. Now you are also moving forward with the same speed of wheel because you are at the center, right? So you won't be able to feel the translation, but what motion you will be able to feel? The circular motion, the rotation. You will be able to see that the point which was at the top has now moved to the bottom and it has now again moved to the top. You are moving forward, wheel is also moving forward, but it's rolling, it's a circular motion. You will be able to observe if you look at it from the frame of reference of its center, right or not? So these are the two motions, translation motion which you can see, which you can feel from this frame of reference of surface, and the circular motion which you can feel, which you can observe from the frame of reference of the system, right? Now, if we talk about the actual motion of any point on this rolling disc, let's see how that looks. As you can see that if we start tracking, observing the motion of any particular point on the circumference of this rolling disc or rolling wheel, we can clearly see that it performs neither pure rotational motion nor pure translational motion. Correct? It is not moving circular. The pattern of motion is not in the form of circles, and it is also not in the form of straight lines. And why is it moving like that? Why any point on the circumference is moving like that? You can clearly understand that from the basic that I just told you, that the motion performed will be a combination of translation as well as rotation. It will not be pure translation, or it will not be pure rotational, pure circular motion. So we are going to discuss more about the combination of translation and rotation, but not right now. Right now, let's just cover some more basics of rolling motion, and then we will come back to this discussion that how this pure rolling motion is combination of two different types of motion. Okay. So we got a general idea of what is rolling, but we have not started any technical discussion yet. Let us start the discussion. And for the discussion, consider that there is any shape which can roll, right? This is a circular plate which can roll. And assume that on its circumference, there is some wire which is winded up like this, right? You can see that there is a wire. Actually, this is the cord of the charger. But suppose it is winded up like this on the circumference of this rolling body. Alright, completely winded up once. Now, as this body will start rolling, and I have attached this particular cord to the ground as it keeps rolling, what will happen? This will unwind, right? Suppose that this cord is sticking on the surface as the body is rolling. So what will happen? This cord will unwind from it, right? So initial condition was this, right? This blue color shows this red colored wire, alright? So as this body starts to roll and as this cord starts to unwind, this is how it will look, right? I have shown a 180-degree rotation. So point which was on the top is at the bottom, and the point at the bottom is at the top, right? And this blue color shows nothing else but this red colored cord that I have shown. So how this body moves, this cord is going to unwind, alright? So this is the basic diagram that I have shown here. In this case, I have not shown the blue colored wire, but here also there is a blue colored wire just like this, right? Initial condition is this, and as it keeps moving, the wire gets uncoiled. Now suppose that this body has rotated by some angle theta, as I have shown here. For simplicity, I have taken theta as 180 degree, right? 180 degree rotation I have considered, but this can be rotation by any angle. It can be 10 degree rotation, 20 degree rotation. Depending upon that only, this wire will uncoil, right? If I have rotated it by 180 degree, this length AB will be a certain length equal to half the circumference. If I rotate it by a very small angle, then this length will be small. If I rotate this theta by a complete 360 degree, then this whole wire will be equal to the circumference, right or not? If I totally rotate it, the whole wire will unwind, correct? So this length AB depends upon theta, and let us say this AB length is S, alright? And now this length SAB, is it not equal to length BCA? What I am saying is that this length S is equal to length AC and B, ACB, right or not? S represents how much wire has uncoiled from the drum, from the plate, and the uncoiled length is this one, AC and B. So I can very much write this for any angle theta, right? Theta can be a small angle, 90 degree, 20 degree, whatever angle. And ACB is a part of the circle for which I can write theta is equal to length of arc divided by radius. Theta is equal to L by R. This I can write for any value of theta, right? Length of arc is equal to ACB, right or not? Radius, let's say, is capital R, and this is theta. So ACB is R theta, right or not? And if I differentiate this with respect to time, then what is ds by dt? ds by dt, rate of change of s. What is s? S tells the translational distance, the linear distance that this body or the center of mass of this body has traveled. This length and this length are same, right? This length is also s, and s is the distance by which center of mass has moved, which tells the linear distance traveled by the center of mass. And ds by dt tells the velocity of linear motion of the center of mass, right or not? So this is nothing but velocity of center of mass, right, is equal to, and this COM I am writing by assuming the body to be uniformly, mass is uniformly distributed, right? So don't go into that confusion that, sir, what if it is not center of mass and all those things. The body that we are going to discuss is having uniform mass distribution throughout. So this is velocity of center of mass is equal to differentiation of r theta. Differentiation of ACB means r theta. R is a constant, so you will have d theta by dt. And what is d theta by dt? Nothing but omega, angular velocity omega of this body. So V center of mass is equal to radius of the body multiplied by angular velocity of the body is the expression, mathematical expression, which is relating the linear velocity with the angular velocity. And this is the condition of pure rolling. Pure rolling. I know many of you will be thinking that, sir, V is equal to R omega, such a basic statement. Why you had to explain this much for V is equal to R omega? You cannot understand it right now, but as we will cover the topic, we are going to cover slipping also. Then you will realize that how important it is to understand very well that this case is of pure rolling. In pure rolling, the velocity, linear velocity of the body or velocity of center of mass is related to the angular velocity of the body. Both of the motions are not separate, they are together. They occur simultaneously. For rolling to occur, variation of V with omega should be in this manner only, such that V by omega is R. If V by omega is not equal to R, it is possible that the body is rolling but slipping also. Backward slipping, forward slipping, different types of slippings can be there. Then in that case, V by omega will not be equal to R, right? So for pure rolling, the linear velocity and angular velocity, the linear motion and angular motion, both of them occur simultaneously and they are related by this mathematical expression. Clear? Now when this rotation will be equal to 180 degree, how much will be the length of S? S will be half of the circumference, right? Pi multiplied by R. 2 pi R is the full circumference, pi R is the half circumference. When this length of travel will be equal to 2 pi R, means the body has rotated once, full one rotation has occurred. This is also one more way to define pure rolling. Pure rolling, that when one complete rotation of the body, translate it by the distance of its circumference. When one complete rotation of body, translate it by the distance of its circumference, means S is equal to 2 pi R. That motion is called as pure rolling. These are the different ways in which you can define the pure rolling, but the gist, the conclusion, I have already told you, and it is an important conclusion. Although I know that some of you will be thinking that, sir, what a basic conclusion, V is equal to R omega, we know since school days. But just wait and let me cover the topic, you will realize that this is one very important expression. So as I told you, that pure rolling motion is a composite motion, is a combination of translation and rotation motion, right? Or rather pure translation and pure rotation motion. Let us understand and analyze this fact using the concept of vectors, and it's a very important approach. Pure translation means we have a body, let's say we have this body, and this body is performing pure translation motion. It is not rotating, it is merely moving forward. This is the surface and it is moving forward on this surface. This is pure translation motion. In pure translation, all the points on this body are traveling equal distance in equal time. So their velocity is same. All the points, including the center, including the point of contact, all the points have same velocity, right? In the direction of motion. So let's say that velocity is v naught. So this is also having velocity of v naught. This is also having velocity of v naught. This point is also having velocity v naught. All the points, whatever points you want to pick, all of them have velocity v naught in the direction of motion, right? This is pure translation. Pure rotation means you have a body, its center is not going to move, rather all other points are going to rotate about the center at the same place. It will rotate like this, right? Like this. Center is at the same place. It's not moving anywhere. This is pure rotation motion. All the points will have different velocity depending upon their distance from the center. For rotation motion, how do we define the velocity? V is equal to r omega, right? So at the center, velocity will be 0. Here, velocity will be in this direction. Suppose it is rotating like this with a velocity of omega. Radius is denoted by r. So this is going to be r omega, right? Let's say this is omega naught. This point will be moving in this direction with r omega naught. This point will be moving in this direction with r omega naught, right? How do you find out the velocity? Take the point, join the point with the center of rotation, and the direction perpendicular to that will tell you the direction of velocity, right? Very simple. So this is how we define the velocity of different points in case of pure rotational motion, right? And this is the point where I would like to not relate, but I would like to differentiate this V is equal to r omega with the V is equal to r omega that I told you. What is this? This is pure rotation. Body is not moving, body is not rolling. And V is the tangential velocity, right? It is not the velocity of center of mass. Rather, center of mass has a zero velocity. This V is equal to r omega. In this expression, V is the velocity of the point which is rotating. R is the distance of it from the center. Omega is the angular velocity, right? This is rotation. This is not pure rolling. So although V is equal to r omega in this case and in the case of pure rolling that I told you, they look similar, but they are totally different. Fundamentally, they both are different expressions. That V is equal to r omega is V of center of mass. That is relating one motion, linear motion, with the circular motion. And this V is equal to r omega is totally rotation motion based. It tells the velocity of some point which is rotating about the center. Getting? So although these two look very similar, but they are fundamentally very much different. That is why I was telling you that you will say V is equal to r omega, sir, this we know already. No, that is different V is equal to r omega. This is a different V is equal to r omega. Alright. So this is how we can define the velocity of different points in pure rotation. Pure rolling is a combination of both of them. The body is translating, center of mass is translating, and all other points are rotating. It is only the matter of frame of reference, right? With respect to rest, the body is moving forward. You will look at a body, it's a very small body which is rolling. You can only notice that it is moving forward, right? But when you look at the motion by sitting on the center of this body, then you will be able to see that points are moving up and down, right? You will not be able to feel the motion of it because you are also moving forward, body is also moving forward. You will be able to feel the rotation, right? So actual motion will be a combination of both of them. This is the basic concept of vector. If there are 3 points, Point O, point A and point B. I know the velocity of A with respect to O. I know the velocity of B with respect to A. Then to find out the velocity of B with respect to O, I need to take the vector sum of both of them. The velocity of B with respect to O will be vector sum of velocity of B with respect to A plus velocity of A with respect to O. Same is true for acceleration also. Same is true for position vector also, right? These are the basic concept of mechanics that we have already covered, right? You can modify this equation rather. You can write velocity of B with respect to A is nothing but velocity of B with respect to O minus velocity of A with respect to O. Right? We have just brought this one on the left side. Now this obviously you will be able to recognize faster, relative velocity concept, right? So this concept, same concept we are applying here, that in case of pure rolling, if we want to know the resultant velocity of any point, then what we need to do? We need to find out the velocity of that point with respect to the center, and then we need to find out the velocity of center with respect to rest. So suppose this is point B, this is point A, and we are at rest at point O. We want to know, in case of pure rolling, we want to know the velocity of B. This is pure rotation. I am not talking about pure rotation. Suppose this body is doing pure rolling. Alright. Remove this pure rotation part. Then suppose this body is doing pure rolling. I want to know the velocity of B. What I will do? Velocity of B with respect to A I will consider. That I will consider from rotation concept, because with respect to A, this body is rotating only. It is not moving with respect to A. With respect to A, when you are sitting at the center, it is only moving. You can only see the rotation. You cannot feel the movement because you are also moving ahead. Right or not? So with respect to B, if I want to know, with respect to A, if I want to know the motion of B, then that is pure rotation. And now I want to know the rotation of the movement of A with respect to O, which is pure translation. So movement of B with respect to O will be vector sum of movement of B with respect to A plus movement of A with respect to B. This movement of B with respect to A is pure rotation. Movement of A with respect to O is pure translation motion. So resultant movement will be vector sum of both of them. That is pure rolling, right? So what you have to do to find out the resultant of this motion, you need to take the vector sum of both of these. Vector sum of pure rolling and pure rotation. That will give you the overall picture, what is going to happen, the vector sum. So in vector sum, direction plays very much importance. If both the directions of vector are same, they are added. If it is opposite, they are subtracted. If it is having some angle theta, then you have to find the vector sum by applying the triangle law or the parallelogram law, right? So let's consider the topmost point. Here it is moving with velocity v naught. Here it is moving with velocity r omega naught. So their resultant, when you add them up, the resultant will be moving ahead with the velocity v naught plus r omega naught, right or not? If you look at the bottommost point, this is moving ahead with velocity v naught. This is moving backwards with velocity r omega naught. So at this point, the resultant will be v naught minus r omega naught, correct? Consider these points. Let's say this point. This point here is moving ahead with a velocity of v naught. Here it is moving up with r omega naught. So here you have to take the resultant v naught and r omega naught. The resultant will tell you the direction of velocity. Its resultant will be somewhat like this, right? The resultant vector. That is the resultant velocity of this point at this instant. Similarly, for any other point you pick, it does not have to be on the circumference. I have taken these points on the circumference. It can be any point. It can be this point also. It is also having velocity v naught. This point here, it will be having a velocity in this direction, right? R, let's say this is R dash. So R dash multiplied by omega naught. So its resultant here will be v naught, and this is R dash omega naught. Resultant of both of them will be the velocity of that point. Simple vector sum you have to take, right? So this is the vector analysis, and very important analysis of pure rolling. So to summarize the discussion, the total velocity can be represented as velocity of center of mass plus velocity about center of mass. Velocity of center of mass is this, velocity about center of mass is this, and this is the vector sum, right? Similarly, total acceleration is acceleration of center of mass. The linear movement, it may have some acceleration, velocity may be changing with the time, right? So you may have some acceleration value of the center of mass plus acceleration about center of mass. In this case, the rotational speed also may change, it may increase or decrease. So just like we write V is equal to R omega, we can differentiate it to get A is equal to R alpha, where alpha is angular acceleration. So this value is going to come here, R alpha, just like R omega was coming here, right? So this is total acceleration. And moving ahead, total kinetic energy also is the sum of the kinetic energy of both the cases separately. The kinetic energy of center of mass, which is half mv0 square, half mv0 square, plus kinetic energy about center of mass. About the center of mass, it is performing rotational motion, for which we have half I omega naught square, where I is mass moment of inertia, which will be different depending upon the shape of the body, how the mass is distributed. We have already discussed that in detail in mechanics, right? Now, in this case of pure rolling, if I ask you that how much is going to be the velocity of center of mass, the velocity of center of mass, how much it should be? Apply the basic concept that I have already told you. It is nothing but the radius of the body multiplied by the omega with which it is rotating. It is rotating with an angular velocity of omega naught, right? This is also rotating with the angular velocity of omega naught. Basically, you have given a velocity omega naught to it, right? So this is how they are related with each other. And how much is the velocity of center of mass? Just observe it. It is V naught, right or not? So this is nothing but V naught here. So V naught is equal to R omega naught in this case. And if you look at this point, the point of contact, how much is the velocity at point of contact? V naught minus R omega naught, which means the velocity here is 0 since both the values are equal. It's a very interesting conclusion. In case of pure rolling, the bottommost point, or it is best to call it point of contact. It's not necessary that it will always be the bottommost point. If the surface is inclined, then it may be some other point. The point of contact will always be having 0 velocity. It will always be at rest. The whole body is moving, but point of contact is at rest. And this conclusion, in the beginning, it may not come very intuitive to you. You may think that, sir, how is it possible? Whole body is rotating. Center of the point of contact also, it is, sir, moving. How you can say it is at rest? No, it is at rest. I can prove it in different manners, in different ways. Consider the case of any tank, the tank of army. You would have, I'm sure you would have seen it in movies, if not in real life. Those tanks have not the regular wheels, they have caterpillar tracks. Have a look at this image and this video. So you can see that how the tanks are moving ahead. They have a different type of wheels which is called as tracks, caterpillar tracks. And you can see that the part of these tracks which is in contact with the ground is at rest. Right? This track on which this whole tank is moving ahead, the part of it which touches the ground is at rest. And in the same case, let us modify the shape of it. Suppose the area that you have with you is not that long. It is a very short area, very small area, almost a point. And also assume that the shape of this track is also circular. So right now you have a situation like this. It is in this shape, right? But assume that this part of it, which is on the ground, which is at rest, It is very small. It is made up of very small points, right? Consider that now it has reduced to only a single point. And obviously that point will be at rest, since all these points are at rest. We are only modifying the shape. We are not changing the mechanism of movement. We are only changing the shape of the tracks, right? So every point is at rest on this part. Consider any small part that is also at rest. And now just change the shape, this shape, to make it a circular shape. Proved or not? The body which is moving forward, the point of contact is at rest. Still not convinced? Let us have a look at another mathematical way. Let us have a look at this shape. This is a polygon of finite number of sides. Have a look at this polygon which is trying to roll ahead. You can very clearly see that the point of contact is at rest when it is rolling ahead. Because in this case, point of contact is pointed. You can clearly see that it is very sharp and pointed, and about this point the whole body or the whole object is rolling forward. Now just modify the shape of this polygon. Keep increasing the number of sides. Keep increasing. Increase by 1, 2, 5, 10, infinite. What is going to happen? What shape you will get? You will get a circle. Because what is a circle? Circle is nothing but a polygon of infinite sides. This can also give you a feel that yes, in the circle, although it looks very smooth, it does not feel that it is rolling forward. But yes, about the point of contact, it is rolling forward. The point of contact is at rest. So as we discussed, it's an important point to remember that the velocity or instantaneous velocity of the point of contact will be zero. Point of contact will be at rest. We have proved it using vectors, we have proved it using our logic, and also using geometry. It's an important conclusion which will be used not only in mechanics but also in theory of machines.